Good morning. So we'll continue today with rheology and building on what we've had so far this week. So I'll come back, refer back to some of the earlier talks. So rheology, and you'll see how in this particular case I define rheology. It's actually quite broad, and I'll only touch on parts of it. Patrick Cordier, I don't know, will continue with this. I don't know where he's sitting. I saw him this morning sitting here. So he'll continue with this. So again, I'll refer to upcoming talks as well. I just wanted to point out, so this is work, long-standing work that I'm collaborating with, particularly Ian Jackson, and then one of his current students, Chris Klein, at the Australian National University. So you'll see the seismic property work in particular is done by Ian and Chris. So outline very briefly fundamentals of defects. Why do we have defects? And I'll touch on some of the defects, in particular point defects. And then, as I said, line defects, that is dislocations, Patrick will cover. Then I'll point out something that's a little bit of a new thinking here, that there's a difference between intrinsic and extrinsic defects, and I'll define those, intrinsic versus extrinsic. Extrinsic basically meaning impurities, and in particular for water, the effect of water on the rheology and seismic properties. It turns out extrinsic defects, impurities in the olivine, are very important. So the work that we're doing is pretty much all done on olivine, right? So that's more easily accessible, right? Perovskite, at least the silicate perovskite, is not stable at relatively low pressure. We do our experiments where we need to resolve stress and strain with very high fidelity at relatively low pressures, gas pressures, so we can't really work directly with things, bitumenite, perovskite, for example, or any of the other high-pressure polymers. Okay, so seismic properties then, continuing from that, and then I'll point out also something that came up in Miyake's talk yesterday. You know, we need to account for continuum of relaxation times or for continuum of deformation timescales. So I'll try to cover all of this. One aspect why this is so much fun, at least to me, is this is a polarized light image. So you're looking through a thin section of a rock. You can see when the light is polarized, you can see the interference colors, and they look really beautiful. At the same time, it also reminds you that when I then go on and talk about spring and dashpot models, right, this is really what we're trying to model, right? So in particular, when we're talking about flow, right, you can sort of see that the olivine here, this is a single grain. The olivine is elongate. That's the expression of deformation, right? So the materials, when we, as I said, talk about spring and dashpot models, that's really what we're approximating. So that's a little bit in the background, right? The real materials are relatively complex. And this sample here, again, beautiful xenolith. This is a bit larger here. You can see the olivine pale green. Then you have some darker green in here. That's Kleiner pyroxene. Right here is orthopyroxene, and then here these shiny ones are spinels, right? So these are all in there. It's a polyphase aggregate, whereas all the experiments will have a little bit of orthopyroxene, but for the most part, I'll be talking about olivine. So, right, jumping in from these beautiful minerals, you know, to the very basics of physics. So Hooke's law here, the idea is that if you apply a force, then you get a strain out of it. So in physics, you know, force and distance or elongation of the spring. In geology, of course, we talk about stress and strain. Essentially what I'll address in this talk is this spring constant here, right? So that's Hooke's law, is the proportionality between force and elongation. So twice as much force, twice as much elongation here. And what you're really measuring with this experiment is the spring constant. So if you apply that, so one important point is that the strain here, and I'll come back to that as well, the strain here is instantaneous and recoverable, right? So as you remove the force, you get all of your strain back. The spring goes back to its original elongation. More geologically, right, the same Hooke's law here is expressed as stress and strain, epsilon here, and then the spring constant are these moduli, right? So Young's modulus more for engineering applications, and then what we are mostly interested in is the shear modulus, but also the bulk modulus. So S and P waves, as you know, depend on bulk and shear modulus. The crystal lattice, Jennifer Jackson covered that. Essentially, the positions of the atoms in the crystal lattice is from quantum mechanical, you can go back to as basic as you want here, is the potential here and versus the distance between the atoms is the result of superposition of a repulsive. So you have charged, if this is sodium chloride, you have charged ions, so you have repulsive energy and an attractive energy. And the superposition of the two, that's the smooth curve here, that has a clear minimum, and that's where your equilibrium position, that's the distance between the atoms in the crystal lattice. And that's important. You can see that the springiness might come from the fact that when you try to compress this, for example, right, you're trying to move here this equilibrium position, up the potential well, essentially, right? So that's the resistance. That's in essence very, very simplified where this elastic modulus, the spring constant, comes from. So deformation then, right? Here's Hooke's law again. Stress is modulus times strain. Here's the stress, here's the strain, the shear modulus, and you can clearly see that solids flow, right? You can't see that as directly with the mantle. You have to take plate tectonics from observations. But here, the glacier, it's pretty visual that you actually have crystalline ice, a solid, that flows. And you can calculate. So, right, the shear modulus of ice is roughly 4 gigapascals, 4 times 10 to the 9 pascals. The strain, just for order of magnitude, we just say a strain of 100%, so epsilon is 1. So basically here, the stress for the flow should be of the order of the modulus, right? That's what we're saying. We have clear deformation here, so if we deform a spring, we need to apply a force that overcomes the spring constant. But at the same time, you can calculate what the stress actually is, what drives the flow of this glacier. Right?
I'm a little bit confused. You use the word flow, and this is an equation without time in it.
Wow, okay. You'll see where this is going. So, oh, sorry. So Michael was asking, I'm talking about flow, but this is an equation without time. Right? So the point is, in order for flow to happen, I have to overcome the spring constant first. So I need to have a minimum force, basically, to overcome the spring constant. You'll see where this is going, right? So yes, this is not describing the flow. I'm just trying to get at how much force do we need in order to get the flow in the first place, right? So, right, so driving force is gravity here, and then we can calculate the pressure or stress is just rho gh, density times acceleration of gravity times the thickness, right? The thickness of the glacier. So density of ice, just round numbers, 1,000 kilograms per cubic meter, acceleration due to gravity. Let's assume a thickness of 1,000 meters. And then you get a stress that's about 10 to the 7 pascals, right, with these round numbers. So that's basically you have to compare. Here's the spring constant, and here's what we actually have available to drive the flow, right? So there's clearly a bit of a problem here. We have 2 orders of magnitude, right? So again, what Michael was asking, we need to overcome the spring constant in the first instance in order to get flow, but apparently we have a really big problem, right? And the problem is even worse if you think about mantle convection. The minerals, so olivine, for example, the shear modulus is about 80 gigapascal at room pressure and temperature, so they are of the order of 100 gigapascal. They get shear modulus increases as you go into the Earth with the polymorphs. But the convective stresses are of the order of 1 to 0.1 megapascal, right? So many orders of magnitude difference here. Megapascal 10 to the 6, gigapascal 10 to the 9, right? So we clearly have a problem. We can't, the perfect single crystal elastic constants can't be what's accommodating the flow in the mantle, right? And in particular, we need to modify these perfect elastic moduli. We need to have defects, right? They can't be, perfect, because otherwise nothing would ever happen, right? So that's the reason why we need to talk about defects. Where do the defects come from? Why do we have defects in the first instance? And for that, we can actually look at very basic thermodynamics. Again, you've seen this diagram here before, the energy here expressed this time instead of the potential versus distance. And the energy of the crystal, so system, in this case, the crystal, it's the potential energy from the bonding, right? So sodium chloride, again, the simplest example, you have energy That's the energy that's stored, basically the reduction of energy when you bring sodium chloride together. And in addition to that, we have, of course, temperature. And so we have kinetic energy. The atoms aren't fixed at their equilibrium positions, but they vibrate around in this potential well. Right? And that's essentially where an activation energy is coming from. The higher the temperature, the more they move around. So if you think about diffusion, where they have to hop from one potential well into the next, the higher the temperature, the easier it is to hop from one potential well into the next. So diffusion is temperature dependent. It becomes faster as temperature increases, right? So going back to the internal energy, interatomic bonding plus the vibrational energy. And then in the Earth, of course, that's a little bit the difference to a lot of engineering applications. We also need to always consider a pressure, right? There's always pressure increases fairly rapidly in the Earth with density. So that pressure also modifies the bonding environment or has an effect on the bonding environment on the internal energy. So pressure is always in the background here. So that's the internal energy, but the other part that we need is entropy. Right? So entropy, a measure of the disorder, and from the second law of thermodynamics, you know that entropy increases. So if you have a gas in one chamber, if you open up a valve to the second chamber, the gas tries to occupy all of space. Or a different entropy is here, the configurational entropy. The entropy is at a maximum when you have this mixture of compound A and compound B. And one way to think about this, right, so here the entropy is very low. That's the parents' room. It seems very ordered. On the other hand, right, that's the maximum entropy here, the kids' room. That's the more natural state, right? So, right. So entropy, right? That's an important consideration. And entropy comes in for the defects. Why do we have defect? So if you want to take the perfect crystal, take one atom out, right? You pay the penalty. You have lattice distortion. Obviously, the perfect crystal is not perfect anymore, right? Your bonds are disrupted. So imperfect satisfaction of bonding. So this enthalpy, right, the energy of the crystal increases because you make that defect. But also, right, the entropy, right, you make it more disordered. So you have an entropy gain, essentially. The entropy increases. And the Gibbs free energy here, the total energy of the crystal, is this enthalpy term, and then the entropy term has a negative sign in front of it. So as the entropy increases, right, the Gibbs free energy decreases. So you'll have to look at both of these terms, and it turns out that if you plot that very schematically here, defect concentration versus energy, right, defect concentration, as you put more defects in, the disorder increases, so the entropy increases. But going back to the room, right, if you just have a perfectly ordered room and you throw a few socks around, you get a very quick increase in entropy here, right? But then adding to a totally messy room a few more socks doesn't make much of a difference. So this, in effect, the entropy term here sort of shallows out, smooths out. So or adding a lot more defects doesn't make much of a difference. The enthalpy, on the other hand, every time you take an atom out, you get a penalty, basically. You pay the same price, more or less. That's very schematic. But the entropy increases here in a straight line, right? So schematically, then, the Gibbs free energy will have a minimum here at a finite defect concentration, right? From the superposition, right? These two terms in the Gibbs free energy will give you a finite defect concentration, and you can calculate that, what that defect concentration is. Right? So for small defect concentrations, you get a greater enthalpy increase, but you get the entropy gain. And so you have a finite number of, and these are point defects that you're gaining here, right? So these are the kind of defects that I was referring to, point defects. So again, you have your sodium chloride lattice. And the types of defects you can have vacancies here or interstitials. You can see that's a Frankel pair here. So you have a vacancy of sodium and you have an interstitial of sodium. The key part and this is behind later on when you talk about deformation, the key part is that you also always have to have charge balance, right? You can't really have a charged crystal. That's very unstable. So charge balance And you can either do that by a pair of vacancies in the interstitials, or you can do that by having vacancies of both chlorine and sodium, right? Then again, you have charge balance. And these defects from the perfect lattice that involve just the original constituents here in the crystal, these are intrinsic defects. Right? But yeah, this is a semiconductor gallium arsenide. In addition to intrinsic defects, the semiconductor properties, for example, depend also on doping with impurities. And you'll see later on, I'll come back to that, that's essentially what we're doing with the olivine that we're deforming as well. We're doping with impurities. These are extrinsic defects. And you'll see that extrinsic defects, in addition to the intrinsic defects, can have a very large effect on the properties of the material. So dislocation, you can thermodynamically then calculate how many of these you have, right? That was the balance between entropy and enthalpy. There's a different type of defects. These are point defects. You have line defects, and Patrick will be covering them. These are dislocations. These are, as you can see here from the scale bar, these are more macroscopic, so we can't describe them by thermodynamics anymore. We don't have a thermodynamic reason for having defects. It turns out these are directly created by deformation itself. Yeah, so I'll just point out we have line defects, and then line defects here, so these dislocations, very briefly, you can visualize that as an extra half plane in your crystal. The reason why I want to mention that is then you can imagine stacking those line defects here, and you can see what happens to the crystal lattice, right? So in a sense, you're again putting energy into it, and you can see that, again, you're distorting the crystal lattice. In particular, you're misorienting one side of the crystal relative to the other side. And in this very basic model here, if you put enough of these in, right, so this misorientation angle here depends on how closely spaced these dislocations are. If you put enough of them in, you get eventually a grain boundary, right? The two sides of the crystal are sufficiently misoriented relative to each other that you have a macroscopic misorientation, and we typically define misorientation, so a separate grain, distinguishing one grain from the neighboring grain in these polycrystalline aggregates, if the misorientation is something more than 10 degrees. And without going, I'll have one slide coming up that looks at this issue a little bit, why we picked 10 degrees. If you calculate essentially for larger misorientations, the energy here doesn't change very much anymore. You get the greatest energy penalty when you start putting in the initial misorientations to generate subgrain boundaries. And then by the time you're at 10 degrees or larger, there isn't much energetic difference anymore of the grain boundary. So we say anything that has a misorientation more than 10 degrees, although the 10 degrees, it could be 12 degrees or something like that. That's not a fixed number. But that defines a grain boundary. Yep?
In your picture, in your tilt boundary or your subgrain boundary, the dislocations are evenly spaced. And I'm curious if that's a property of grain boundaries, if they are indeed a two-dimensional lattice of defects?
No, I'll get to. So yeah, right. So we're continuously floating between these idealized models, which come a lot from material science, or more in particular metals, right? This is where a lot of this vocabulary, a lot of the background was first developed for metals, in the 30s and continuing on. So this is a bit too idealized. I'll show pictures of grain boundaries. It turns out grain boundaries in olivine are not characterized by dislocations, although Patrick might, yeah.
But the answer is on the right. You see that the misorientation is linked to the spacing of the dislocations. Yeah. So if you have a constant misorientation across the boundary, so then you have a constant spacing of the dislocation. If you have a change in misorientation, then the boundary will adapt and the spacing will change.
Right. So, so a little bit, right, you can obviously see this is very much simplified, right? But it gets a few points across. There's a few important lessons in here, even though the details might then be more complicated, right? And, so again, going back to what you can actually see, subgrain boundaries in quartz, right? So you might have looked at similar images. You can see, or this is just light micrographs here. Olivine shows also very nicely subgrain boundaries. You can see that these are typically not straight, right? There's a lot of grayscale variation, so there's a lot of variation. So it's, and at the same time, right, that's 0.25 micron here, whereas before this, we're talking about lattice spacing. So I'll point out, and this will come up, there is a usefulness to these simple pictures, but you can only take them so far. And of course, in general, we don't have these perfect tilt boundaries, right? There's a twist component. You can imagine that the two halves are also twisted relative to each other. So the boundaries will be much more complicated than that. Right. So grain boundaries, why should we look at grain boundaries? So they're planar defect, right? So we had point defects, we have line defects, and we have planar defects, right? So in terms of, the Earth is not a perfect single crystal. We need to take into account all of these, and grain boundaries in particular are important. That's behind a lot of the measurements that we do of seismic properties. They all refer back to grain boundaries. That's why I want to spend a little bit of time on this. They're always present, and very briefly, I won't go into the details there. When you have deformation, you can see that very nicely in the subgrain boundaries in quartz. When you have deformation, you're putting energy into the crystal. You're generating dislocations. These dislocations in the end will accumulate to form subgrain boundaries and eventually form grain boundaries. So in the Earth, where you have convection, you have ongoing deformation. So you will always have grain boundaries present, right? So there is a discussion whether the inner core, for example, is a single crystal, and I don't know where seismically that stands to explain anisotropy, but in a convecting system, right, where you have deformation, you will never have a single crystal, right? Because you're always putting energy into it and you're reducing the grain size. Yeah. So grain boundaries then affect diffusion, and I'll have another picture. You can sort of, again, imagine, in comparison to the perfect crystal, moving or diffusing atoms along the grain boundary is faster, right? The grain boundaries are not as ordered. You have faster diffusion, and therefore this faster diffusion will also affect deformation. Right? And in turn, seismic properties, and I'll spend quite a bit of time on that, and then also electrical conductivity. So basically everything that we measure, everything that we care about rocks is modified by the grain boundaries. And so to visualize that, to me, that's very interesting. So coming back to the distinction between a subgrain boundary and a grain boundary. So this is a partially molten sample. And it turns out that the melt is a very sensitive indicator of the grain boundary energy. So the subgrain boundaries, in this TEM image, you can see dislocations here. So the subgrain boundary is slightly inclined to the transmitted electron beam. And you can see the individual dislocations here. Here you have melt that's quenched to glass, but at high temperature, when we ran the experiment, it was melt. And you can see that this dihedral angle, which is a consequence of the force balance at the interface between the melt and the solid crystal, the dihedral angle is very large, meaning that the grain boundary or the subgrain boundary energy is relatively low. The melt does not want to penetrate it, right? The melt gets expelled from that subgrain boundary. If you compare that, what I call here a high-angle grain boundary, we don't know what the misorientation is exactly, but these two grains here are misoriented by more than 10 degrees, right? Typically, misorientations clustered, or the peak is around 90 degrees for these orthorhombic systems. So the typical misorientation across the grain boundary is more like 90 degrees. A high-angle grain boundary, and you can see that the melt in this case penetrates quite deeply onto the grain boundaries. You can see that this dihedral angle here is quite different from this dihedral angle, right? And that's a sense that the subgrain boundary is substantially lower than the grain boundary. Right? This bright line here, there is no melt here. You can see here on this side the grain boundary is a little bit inclined with respect to the electron beam. So this is just an effect of the imaging conditions here. So, right? So grain boundary energies, and then, this is a polycrystalline aggregate. This is sort of our view how the metal looks like. This is very, of course, idealized. This is more material science. We make these olivine grains, and initially they're very fine grains. So the scale bar here, 1 micron. The grains are almost perfectly hexagonally shaped in this particular case. And you can see we have a few dislocations present, but for the most part, the defect that we have in here are just grain boundaries. And these, yeah?
I was going to ask what that is.
Yeah, these are pores, right? So these white areas here, these are pores. At the relatively low pressures, 300 megapascals, and there's no melt in this sample, we can't fully get rid of the pores, right? It takes quite a bit of higher pressure in order to get rid of these pores. But you can see that, coming back, the melt, right, the melt distribution is driven by surface energies, right? So the melt will be at every 3-grain edge intersection here. So if you had melt in the system, we'd have every triple junction here would have melt on it, right? This is what Laurent actually showed as well. So there's melt at every 3-grain edge intersection, whereas these pores occur patchy. There's lots of triple junctions that don't have pores on them. There's some pores in the interior. You can see the pores in the interior are smaller, so they got trapped early on during grain growth. The larger ones remain on the grain boundary. But because the pores are not homogeneously distributed, we think they're not contributing. We have no evidence that the pores contribute in any way to what we're measuring, right? And that's the key difference to melt. Melt, because of the surface energy argument, affects every 3-grain edge and some grain boundary, whereas the pores are just random and they're not interconnected. So grain boundaries, yeah, and that this is still ongoing research what the structure is of the olivine grain boundaries, right? So there's many different approaches, many different models. We've always come from the imaging. Again, that's a transmission electron microscope image, and this is a very high resolution image. You can see these are actually lattice planes here, right? These are individual lattice planes, the 0, 1, 0 lattice planes in the olivine. They have the greatest spacing. They're the easiest to image in a transmission microscope. Here, the orientation of this grain is different. You can't see any lattice planes because the orientation is different. The 0, 1, 0 planes will be somewhere else, and you don't see them. This is the grain boundary, and this is work that John Fitzgerald at the Australian National University has been doing for a long time. If you have this grain boundary here perfectly parallel to the beam, you get the minimum width, and then it turns out that the grain boundary here is about 1 nanometer wide, right? So how representative is, as I said, we're still looking into. This is something that's still being debated. And there are now also these ab initio models that, this is a model of an olivine, again, from 2012. You can see the point here is that the grain boundary is less ordered than the grain interior, right? It's a defect. It's less ordered. These empty spaces, of course, won't be exactly empty, but you can get the idea that if you want to put trace elements onto the olivine, you'll have a higher concentration of these trace elements in the grain boundaries relative to the grain interiors. And in terms of transport properties, you can see that diffusion along this grain boundary is faster than diffusion through the grain interior, right? That's why these grain boundaries are so important. Less ordered, faster transport properties. So moving on to deformation and flow loss. By the way, yeah, just ask questions if I'm going too fast here. A first principles derivation, a physical model for deformation based on point defects. And this leads to these constitutive equations that have come up a number of times that relate strain rate to stress. So now we're getting actually a time in there. So this is the proper equation for deformation. And one example, a book where you can look that up, of course, that goes much further back than this, is Poirier, Creep of Crystals. That's a relatively thin book, quite some time ago, but the basics are still there and are relatively nicely explained. So there's a number of other books as well. So the idea is that you need a differential stress, so a stress difference. So you have this very idealized crystal here. You have two sides, A and B, and you have a maximum compressive principal stress here across B and a lower stress across the face A. And this is where these point defects become important. The difference in stress concentration here, depending on which side you're on, which the orientation of the side is with respect to the applied stress here, that modifies the point defect concentration, right? So this stress difference here modifies the point defect concentration, and then basic chemistry, right? If you have a difference in concentration, you'll try to diffusively equilibrate that difference in concentration, right? And that in the end drives diffusion, right? So the very basics, thermodynamically you can show that you have point defects. The important point here is that a stress interacts with the point defect density, right? So that's the point to keep in mind. That the rest is then more or less geometry, how you diffuse and properly account for everything. But the important point is that stress causes a change in concentration and therefore causes diffusion, right? That's schematically indicated here. You have vacancies diffusing in one way, and then you have to have, for charge balance, the counterflux of atoms, right? So if you diffusion of vacancies in atoms, yeah, the compressive stress at B reduces the number of vacancies. You can imagine that. And the tensile stress at A increases the number of vacancies. So you set up a flux here. And that macroscopically then over time, right, if you keep that up long enough, you keep up that stress long enough, you'll have a change in shape, right? Because you're diffusing atoms here and you're diffusing vacancies here, so you'll have a mass flux, right? The net effect is then that you change the shape of the crystal. So without going through the geometry and everything else, that's fairly straightforward. The point is differential stress, concentration gradients, and you set up diffusion. The length scale here, this is the key part, right? The length scale is the grain size. You diffuse from one grain phase to the other grain phase. So the time it takes for the diffusion to happen depends on the grain size. So any constitutive equation then will have the grain size in it, right? Because the diffusive length scale is dependent on the grain size. And then the other part here, the diffusivity, this is what I was mentioning earlier. The diffusivity in particular depends on temperature, right? This is where the activation energy in the constitutive equation comes from, that the higher the temperature, the faster diffusion happens, right? So how fast that transport happens here depends on temperature. And then the flow law or constitutive equation, although I have to say in the end when we do experiments, right, what we measure is the strain rate, we know the applied stress, we know the temperature, so, and we can measure the grain size. Then in the end what we have left is this activation energy, right? That's what we determined from the experiments. And then also this pre-exponential constant. And that pre-exponential constant, right, so here is the proper form, so you have the atomic volume in here, you have the self-diffusion coefficient in here, that gives you essentially the activation energy, and this PV term again is the pressure dependence of it, so you have temperature and pressure dependence in here. That's the proper equation. You can see that you still have this A in here. In the end it becomes semi-empirical because we measure what we can and then fit these other parameters. In particular, A sweeps up things like the ds naught, the initial self-diffusion coefficient, atomic volume, and so on. It's all swept into this parameter A that we just measure experimentally, right? So in particular, there's a lot of effort being made. Ideally, of course, if this is diffusion, right, the activation energy that you measure here should be that of diffusion. But then it depends, well, I'll get back to that, diffusion of what? Right, so experimentally it's more efficient, to fit to this equation. You can see, right, strain rate here, stress is linear in this particular. So if you go through the derivation here, you end up with a linear stress dependence. The stress here is the differential stress, right? Sigma describes the differential stress, the difference between the two phases, and you can see here the grain size dependence comes out of the geometry of the problem. So you have a squared grain size dependence for diffusion through the interior of the crystal. Right?
Is this because it's in a plane? Or why is it square?
No, I mean, so that's the standard structural geology. Basically, you ignore the third stress is intermediate, so you really, in the end, it reduces to the flow from one side of the crystal to the other side, and the third dimension doesn't change ideally, right? So no, I'll get back to that squared grain size dependence. Yeah?
This is maybe a silly question, but you have a finite... question, but you have a finite number of vacancies in the material, and some migrate to the low, the low stress side.
Yeah.
Does it change with time then? I mean, is there some time dependence to that flow law that once the defects migrated a certain amount, the vacancies migrate?
No, in the end, you also, again, thermodynamically generate defects, right? So it's you can go through the basic thermodynamics. So in that sense, there's no time dependence to it, right? So you can keep doing this forever. Yep.
So how does the porosity play a role in that relationship? I assume because it would be affected by the stress as well.
Not exactly. So as I said, the porosity is a bit of an artifact in these. I mean, the theory is derived for perfect polycrystal, right, without porosity. The porosity again is not interconnected. It just hangs around in a few places, so it doesn't really make much of a difference. Melt. That's why I emphasize melt. Melt is at every 3-grain edge intersection. If I have time, I'll get to that. Melt substantially enhances diffusion, right? But the key part is the melt is interconnected, whereas the pores, are internal or at some triple junctions they really don't make a difference. Okay. So going back, diffusion is very important in this problem. Going back to an olivine structure, right? This is something that you saw talking about mineralogy. You have this tetrahedrally coordinated silicon, octahedrally coordinated M sites, so iron and magnesium, and then you have these oxygens in here. Right? So in the olivine structure here, you have SiO bonds that are much stronger than MgO bonds. So if you think about diffusion through the crystal, and if you think about time scales, right? So the slowest part to diffuse in the crystal will likely be these silicons, right? Because they're the strongest bonded, they have these 4 oxygens, and that's an exploded view. They're surrounded by 4 oxygens. So if you want to diffuse these different atoms here, most likely oxygen and magnesium will be more mobile than silicon. And then, the lattice spacing, indirectly, you can have also anisotropic diffusion because obviously the lattice doesn't look the same in every direction. So if you do diffusion measurements, so here is diffusivity plotted versus temperature. This is a compilation that looked at a lot of different types of diffusion in different minerals. Here is the interior diffusion, right? Silicon interior diffusion, and then here is grain boundary diffusion. Right? So this is where the grain boundaries become so important. The grain boundary diffusion, so silicon diffusing along grain boundaries in olivine, so this green line here is the olivine, is much faster, at lower temperatures here, so at the top is absolute temperature. You can see many orders of magnitude faster diffusion along grain boundaries than along the interior. And the other part is magnesium diffusion is along grain boundaries is faster than silicon, and oxygen diffusion is even faster, right? But if you want to deform the whole crystal, you have to diffuse all of the constituents, right? You can't just diffuse oxygen. You won't have olivine left anymore. So in the end, diffusion then is rate controlling during that deformation, right? During diffusion creep, diffusion is rate controlling, and it's the slowest species, silicon, along its fastest path. And so here you can see, right? So there's grain boundary diffusion, and it turns out that if we do experiments and fit our data to the grain size that we measure, we don't have an exponent of 2, we have an exponent of 3. And again, that exponent of 3 for the grain size here falls out if you do the geometry diffusing along grain boundaries. So instead of, in this ideal, right, so instead of diffusing through the interior, you diffuse along the grain boundaries. And if you do the geometry of this problem, you end up with a cubic grain size dependent, not a squared grain size dependent. So experimentally, we can distinguish between grain interior diffusion and grain boundary diffusion. And pretty much what is almost always observed, except for, in particular circumstances, very, very fine-grained materials, the grain boundary diffusion is so much faster than grain interior diffusion. So you always end up with this cubic grain size dependence.
Uli, this doesn't look like a linear plot, but your equation is linear. The relationship between strain rate and stress.
Which part does not look linear? The curves here.
Well, the vertical axis is a log scale. The horizontal
is a log scale.
Oh, it's log 2.
Yeah, and the fact, so this plot is a little bit complicated, right? So these lines aren't exactly, there are details to that. These lines aren't straight, right? That's not a straight line. You can see the curvature changes. And basically, right, so strain rates, time, I also have grain growth. So I can measure the grain size before the experiment, the grain size after the experiment. And in this is the fit then to all of the data. I include the effect of grain growth, right? So grain size, because it's cubic, has a very strong effect on diffusion creep, right? So I need to include grain growth, the effect of grain growth while I'm deforming, right? While I'm deforming, I also have grain growth. I'm not producing dislocations in this part. So while I'm deforming, I have grain growth. So I need to, in fact, account for this increase in grain size in order to fit my data. But otherwise, right, so yeah, log plot. This is log stress versus log strain rate. These are a whole bunch of experiments. You can see the temperature from 1150 to 1350. Right? That gives you the temperature dependence, right? This is this E here, what we determine from the strain rate if you fix yourself at a stress here and go up in temperature, the strain rate increases, right? So that's the temperature dependence here. As I said, we measure the grain size, we know the stress and so on. So we can determine these parameters where I have to say, right, so these experiments are all done at 300 megapascal gas pressure. So we don't determine the activation volume, right? 300 megapascal is about 10 kilometers depth, right? In terms of the mantle, that is not very much. The advantage is that we can determine the other parameters here, grain size dependence, stress dependence, this A, very precisely in the gas medium apparatus, because we don't have friction of the apparatus itself, right? In a solid medium apparatus, it's much more difficult to determine strain rates and stresses accurately because you have to account for friction. It's much harder to measure everything. Your samples get much smaller. These are the samples that we deform here are fairly large, right? Yeah?
Think about this in terms of, say, a viscous fluid. And I guess the A, the d cubed, and the exponential term is basically a fluidity, right? I mean, thinking of a constitutive relationship with stress equals viscosity times shear rate, right?
I'll get to viscosity, right? So I haven't really introduced viscosity yet, if that's where you're getting it, but.
Yeah, I was just wondering in these typical experiments what that effect of viscosity would be.
So I'll show that a little bit.
Okay.
Yeah. Yeah.
Just asked that question, and Quentin gave me an answer. Quentin, go ahead. You asked the question. Well, that was the same question. It was the same question that Frank just asked, and you gave me a pretty good answer.
Okay. What? No. So let's come back to that. I'll get back to that a little bit. Right, so there's one more point to this, right? So if you have pure diffusion creep, right, we talked about if you have diffusion from one side of the grain to the other side, you'd predict that the aggregate then also, so each grain then would change shape, right? That's the prediction. That was the model that I started out with. If you have only diffusion going on to accommodate the stress and therefore the strain that you impose, then you should change each individual crystal from, the square in this instance to a rectangle. Right.
Would that change in shape be affected by the crystal system of the mineral that you're deforming? So if it was a triclinic crystal versus obviously, say, isometric crystal, is the change in shape congruent?
So the change in shape actually doesn't happen, right? So this is the point that I'm making here. So this is actually, so you saw the TEM image of the aggregates before deformation. This is an SEM image after deformation. You can see that the grains clearly aren't elongated like predicted like that. So I've imposed a strain of, in this particular case, maybe 10% or something like that. There's no elongation apparent here. And this is a general observation. Grains after diffusion creep, remain more or less equiaxed. Right? And there's some modification if a grain wants to be elongated, like amphibole, for example, or something like that, it'll be elongated afterwards as well, right? So the olivine turns out to be, the grain shape turns out to be more or less hexagonal, but the point is that the grains don't change shape during diffusion creep. And the idea for this, again, going back to the metallurgy and early material science, that actually what happens is that you just have diffusion accommodating the creep, but that a lot of the strain is actually taken up by sliding of grain boundaries past each other, right? So here you have this diffusionally accommodated grain boundary sliding. That's the proper term for diffusion creep, right? You have diffusion, but if you look at this idealized hexagonal aggregate, right? So you apply a stress here, and what happens is that while you have diffusion here along the grain boundaries, you're also switching, right? So you have this switching event. You can see that overall, the individual grains are equiaxed. The macroscopic aggregate is elongated. If you apply a stress here, right, then at the end, you just switch neighbors, more or less. So you switch the sides of the grains, right? And this is where the diffusion happens here. And then in the end, you again have an equiaxed grains, but the macroscopic shape of the aggregate that you deformed is different. Yep.
Are there any signs of pressure solution? Or in other words, is the diffusion faster than pressure solution?
So pressure, what is pressure solution? Pressure solution essentially is, in some sense, diffusion creep, except that typically you also have a fluid present, right? And the fluid will then enhance the diffusivity, and if you have larger fluid pockets, right, you can deposit material in those fluid pockets. But in the end, it's the same mechanism, right? You apply a differential stress, compression on one side, extension on the other side. You diffuse from compression to extension, or the lower, from the higher principal stress to the lower principal stress. So pressure solution is much the same, except that in pressure solution you do observe, right? If you think about low temperature pressure solution, you do frequently observe elongation of the pebbles, for example. So that's, in that sense, a little bit different. The pebbles don't seem to slide, in the examples that I'm aware of, don't slide past each other. Whereas the grains, the observation is that the grains remain the same, have the same shape before and after deformation.
Uli, are there any rotations involved?
No, there's no rotation involved, and that's key, right? So there's the crystal lattice itself, right? So there's no rotation of the crystal lattice. So that's important. So I'm jumping around here a little bit, but you cannot generate seismic anisotropy, for example, by diffusion creep, right? You need dislocation creep where there is rotation involved. Diffusion creep is irrotational in that sense. Right? I'm not sure whether I answered your question, but we can discuss that some more. Right? So that's the importance. So this is, and I'll come back to that for the seismic properties as well. The idea is that grain boundaries can slide past each other, and that at some point you need diffusion, because clearly the rate limiting step is this diffusion. That's what we measure in the deformation experiment. The rate limiting step is the diffusion, but the strain is actually by and large accommodated by this sliding of the grains past each other. So again, briefly extending to what Patrick is talking about. So the constitutive equation here, so we had a linear relationship between strain rate and stress. You can see that as stress increases here, again, log scale, you have a transition, right? The slope here is 1 at about 1. You have a transition to a much steeper slope, n equals 3.5. And that's then the transition to dislocation creep, right? So diffusion, obviously, you diffuse individual atoms. As you'll see, dislocations are much more efficient in imposing strain on the crystal. So if you increase the stress, you ask the crystal to deform much faster. At some point, it switches to a different deformation mechanism here, the dislocation creep. And without going into details, the important part is, since the dislocations are internal to the grains, there's no intrinsic scaling length associated with it, right? So dislocation creep is then not grain size dependent, right? It's grain size independent, but at the same time, because the stress that you impose actually modifies the dislocation density, right? So there's a feedback between stress and dislocation density, right? The defects were not affected by the stress. The point defects were not affected by the stress. They just move. But the applied differential stress does not generate the point defects, right? There is a thermodynamic reason for that. Whereas the dislocations themselves, the dislocation density, how much we have, are affected by the stress. And so you get this nonlinear relationship between strain rate and stress. Yeah?
So what governs the empirical number n, and is that empirical or theoretical, or what are theoretical models to explain it?
That's a great question. So there are, again, so here is a little bit, so you have again, you can look at a velocity with which the dislocations move in the crystal lattice, and you can again derive sort of a first principles equation looking at dislocation deformation, and you get different values for the n from depending how you think the dislocations are generated, dislocation sources and so on. It turns out, though, that most of the models, right, arrive at whole numbers for this n. If you do the experiments, it turns out that n doesn't correspond exactly to any of these models. So in the end, that's right. This is a little bit the tension between these idealized models, which, again, have been derived mostly from metals. Silicates are much different, right? You have the dislocation structures that tend to be more complicated, other processes at play. So in the end, we measure this exponent, and that's one of the fit parameters. So we do the experiments, measure the exponent, and that goes into this equation. So this equation is no longer, the pure material science equation, that in this case, Wertmann creep, for example. Right. So yeah, and then you can come up with deformation mechanism maps. So dislocation creeps. So grain size here versus stress, right? The larger the grain size, the less efficient diffusion is. So you get dislocation creep coming in, right? Because that's more efficient. Grain size independent. That, as I indicated earlier, reduces the grain size, right? The dislocations move through the crystal, form subgrain boundaries, and eventually those rotate and form grain boundaries. So you get grain size reduction. I already mentioned during deformation and diffusion creep, you have grain growth. So the idea is that the grain size in the mantle is, in the end, somewhere near this. This is a piezometer here, but it's somewhere near the field boundary between diffusion creep and dislocation creep. Because you have these opposing effect, grain size reduction in one creep regime, grain growth in the other creep regime. So you have a finite grain size that is determined by these counterbalancing effects. Yeah?
And the time scale for either the reduction or the growth is short enough that we should expect in the real Earth to lie on that line?
Yeah, so, right, so here's strain rate. These are strain rate contours, but there are papers a number of papers that look at this issue. That's also one of the things, right? So you have to measure grain growth rates, and then you look at grain size reduction rates, basically. So grain size reduction due to the energy you put into it. Grain growth is, of course, driven by surface energy minimization, and the idea is that from these models that you end up with some steady state grain size that hangs together more or less. But again, that's something that's still being debated.
Are there any rules of thumb that how pressure would affect these lines in terms of moving them differentially? For instance, if this was at, say, 4 GPa instead of 0.4, are certain boundaries moving, other boundaries not moving?
Right. So So you have the activation energy. That's your temperature dependence,
right? And
that moves. Right. So this is at a fixed temperature here.
Sure.
That moves all of these boundaries around, and then
I'm thinking of pressure, actually.
Yeah, pressure is exactly the same, right?
But is it self-similar? That's what I'm asking. Does the whole diagram kind of translate, or does certain boundaries, certain areas expand relative to others?
So we have one of these equations for diffusion creep, for dislocation creep, for this field grain boundary sliding, for the Peierls creep. Each has its own pressure and temperature dependence.
So it's the relative activation volumes for each process.
Right. That are experimentally determined. So these boundaries all move around depending what the activation energy is, depending what the activation volume is, right? And then also grain size. Okay, so this was all, right, so now we're making the shift. Now we had intrinsic defects, right? Only, the constituents of the crystal. The point of the slide, you don't have to read all of this. The point is, this is an analysis of olivine here from a paper from 2010. And you can see that if you can measure it, the entire periodic table is in olivine, right? The point is, so if you put aluminium, right, 3+ into the olivine crystal, we have magnesium 2+, silicon 4+, right? We're generating defects, right? And you have aluminium significantly, sodium is in the olivine, surprisingly, somewhat, calcium, and in particular also titanium, right? And titanium is 4+, which gets interesting because silicon is 4+, right? So the point of the slide is that these impurities in natural crystals, so the material scientists can control their impurity contents. They don't have to worry about that. But for rocks, we do have to worry about that. And this is an example here. So water is an extrinsic defect. So now we're talking about water in nominally anhydrous minerals, right? Water is not intrinsically part of the olivine crystal structure, but we can incorporate water, or more particular hydrogen or hydroxyl actually, in an OH group, as a trace element. And the way we measure the water content in the olivine, we do a different type of spectroscopy. Instead of shining light, like visible light through the crystal, we shine infrared light through the crystal. And the infrared light is absorbed by this hydroxyl, by the bond between oxygen and hydrogen, right? And then if you then measure the absorbance, so this is wave number, basically you go through the frequencies here, right? You dial through the frequencies. The absorbance of the infrared light is then determined by how efficiently you excite these hydrogen-oxygen bonds. Right? So, and it turns out if you do that for olivine, you get absorbance, and these are the red lines here, at 2 particular wave numbers, right? So the energy absorbance is optimum in these natural crystals from a number of different locations here if you absorb at particular wave numbers here, 3572 and 3525, right? So that then says something about the bonding environment, right, of the hydroxyl. And in particular, if you look at this, again, looking at the olivine structure, right, here's your silicon tetrahedron, various tetrahedra, then you have the magnesium in here. And for this particular absorbance, the defect structure that has been, in this case, calculated from ab initio, from molecular dynamics simulations, is that you get the right kind of vibrational frequencies if you have a titanium, which was on the list of these trace elements in olivine, on a magnesium side, right? And then you have to think about charge balancing. So you have a 4+ ion here on a 2+ side. If you have an adjacent vacancy in silicon, right, you have, again, charge balancing, then you can charge balance the overall defect complex with 2 hydrogens, right? And these 2 hydrogens then, these hydrogen-oxygen bonds, they give rise to these vibrational frequencies, which you measure here in the infrared. Right? So that's an extrinsic defect, and you can see the beauty of this is that if silicon is the slowest diffusing species, here we have another way. Instead of just thermodynamically, now we're making defects by substituting a titanium into the olivine crystal structure. So we have another way of making these point defects. Silicon is the slowest diffusing species, so if we increase the number of silicon-related defects, we can increase the diffusivity. And that's the idea behind these experiments that we did, again, in the gas medium apparatus. So that's roughly an outline. There are a few more details. So if I mentioned for the semiconductor, right, you can change the properties of the semiconductor by doping with impurities. So in this case, we doped the olivine but with titanium to increase the number of point defects. And then we also, in this particular case, we need to encapsulate in platinum to keep the water in there, the hydroxyl. If we deform that, then we get very much enhanced strain rates. And if we do the infrared spectroscopy on these synthetic crystal now, we find that we have the same absorbances at these 2 characteristic frequencies that are typical of this particular defect. Right? So, and yeah, not so much. So we have to look at molecular water in the infrared spectrum. You have this broad absorption region here, that's molecular water. If we fit molecular versus the structurally bound water, the hydroxyl here, we find that we can't fit the molecular water, but we can fit what we call the structural water, the OH groups. The water content, so here's water content as a function of strain rate. So the more water we have in the olivine, the faster it deforms at constant stress. So this is calculated for constant stress. So I fix the stress, increase the water content, we get an increase in strain rate. So in that sense, the behavior is similar to temperature. As you increase the temperature, the crystal deforms faster. As you increase the water content, the crystal deforms faster.
Really?
Yeah.
If I understood you correctly, then the water content should relate directly to the titanium content?
Right.
Did you measure titanium in all of
yes.
these as well?
So I don't want to go into too many details. Yes, we can talk about that more. Yes, it correlates with the. In these experiments, it correlates with the water content. It actually works out beautifully because the Sankala's olivine, which is typically used for deformation experiments, also has a finite concentration of titanium. If you look at the infrared spectroscopy, you get about the right. So the defect structure predicts 2 hydrogens per titanium. So we can determine the hydrogen concentration from the infrared spectroscopy. We can measure the titanium content with laser ablation, and we get about the 2-to-1 ratio.
But if, for example, the olivine were in equilibrium with rutile or ilmenite or a very titanium-rich garnet, then you might anticipate that the actual trace mineralogy of the assemblage would modulate the viscosity of the olivine. Would that be a correct inference? You
need to be titanium. Okay. It depends on the partitioning. It depends in the end how much titanium you have in the olivine. And then, so it gets a little bit more complicated. It also then depends how much water, of course, you have in the system, right? You can have more titanium than you have water, then not all titanium is hydrated. Or conversely, especially at higher pressure, there are many other defects in olivine. So this is not the only defect that you can hydrate, right? But it turns out that the low pressures, you hydrate only this particular defect. So you can have the situation for Sankala's olivine, there's not very much titanium in it. So if you actually buffer the water content at higher pressures, you get much more water in the olivine, right? But at these low pressures, and in particular, the point is that this titanium clinehumite type defect is the first one to get hydrated. Right? That's energetically the most favorable one. So, and that we can show here controls the rheology.
Yeah. My only point is that if you have if you don't know the full mineralogy, the full mineralogy of the sample ultimately has a major influence on the defect structure as well. So there's an important link between petrology and viscosity here.
Yeah. So I want to continue here, so I've got a bit more. And in particular, an important point is that the relationship between strain rate, so this is again the equation, the only difference is that I've added the water concentration here, right? So that's the only additional component. So I have to stick in because the strain rate, what I'm showing here is that the strain rate depends on the concentration of water in the olivine crystal. And that is another component, another factor in here. And this is the exponent. And the exponent turns out to be near 1, right? So 1.2, but if you look at the scatter of the data, we can, it might as well be 1 as well. So that's within the error of the measurement. So that we have a linear dependence of strain rate on water content. And that's important, right? So water isn't magical. So a whiff of water won't automatically make everything really weak. It depends on the concentration in a linear fashion, right? And I've left off the pressure dependence, so the pressure dependence is in here as well. Right? So that's our constitutive equation where we include the water content as well. And just coming back to viscosity, then viscosity is calculated here. That's Newtonian viscosity, right, from the ratio of stress over strain rate, right? So the strain rate, is this, and so you take stress over strain rate. You're left with the rest of this equation, basically what is in your viscosity. So the viscosity, has all these dependencies in it. And I wanted to make one more point, right? So this is linear dependence of the strain rate on stress. If you have a power law dependence, which is shown very vaguely here, the viscosity then depends on the stress itself, right? It depends on all of these parameters, but for power law, so this is linear, but if you have a power law in here, so this n is greater than 1, in this particular case 3.5, then the viscosity that you calculate depends on the stress that you apply. Right? So that's an important point, but again, jumping forward a little bit here. So, yeah.
So why is there a size dependence, a grain size dependence in the last equation?
This is a general equation.
Okay,
so for dislocation creep, this would be 0.
Yeah.
Right?
So because you don't know the diffusion regime, the regime, you don't know this is. Sorry. So you assume that you can have all the previous regime of deformation.
Right. So this is a general equation where so then you just vary. So for diffusion creep, n would be 1, p would be 3. For dislocation creep, n would be 3.5, and p would be 0.
Okay.
Right. But both diffusion and dislocation creep depend on water content. And likely in dislocation creep, you have climb, I won't go into the detail, which is diffusive. So you, again, are back to diffusion.
Uli, you mentioned that you might have too much titanium and not enough water. So would something else then have to replace the OH, like chlorine or fluorine? And so should the FH2O be the sum of all the things that are fitting in where the water is, or the OH?
No, I mean, so with the titanium clinehumide defect, the idea is if you have dry olivine, the titanium actually sits on a silicon side.
Okay.
Right. So there is no experimental evidence that anything else other than hydrogen water has such a strong effect. So we don't. Yeah. Right. So this is just a very brief application of this. You can calculate the viscosity in the upper mantle as a function of water content, right? Green is dry. Then here these units are in ppm hydrogen per silicon. So we do it a little bit differently than a geochemist because we want the effect is essentially how many hydrogens do you have per silicon, right? That's the measure. That's the measure of defects that we have. So that's how we account for it. You can convert it into weight ppm H2O, right? The point here is the shape of these curves, right? This increase in the viscosity here with depth, that's the activation volume. So that's that PV term in the enthalpy, right? And there is debate here. This isn't experimentally settled. This is a relatively high activation volume. Then you get an increase in the viscosity as a function of depth. But that's something that we don't measure in the experiments at low pressure, right? These are other experiments. But if you had 0 activation volume, your adiabat, you have an adiabatic temperature increase, then this curve here would actually, the viscosity would decrease, and you don't end up with this. Here you have a low viscosity zone, right, which is seismically a low velocity zone. And you generate that by interaction of the geotherm, so the conductive cooling here for oceanic lithosphere with the adiabat. That gives you this minimum here, which, again, depends on the activation volume, the slope here. All right, so I wanted to get to seismic properties. So we've talked all about, essentially, convective timescales. Right? Now I want to jump to the other end of this. This is a diagram that you've seen before in a different form, right? Timescale of deformation, so t in seconds. You can see that, 1 second to millions of years. Here, I want to jump to the other end of the timescale, the seismic properties. And again, we do experiments here, except that instead of deforming the sample in compression and shortening it that way, we just twist the sample. And we twist the sample either in a step function or we twist it periodically, like seismic waves, right? You have a sinusoidal seismic wave. We can apply a sinusoidal torque on the sample and measure the properties. And again, temperatures, upper mantle temperatures, the periods of these experiments are now between 1 and 1,000 seconds. So this encompasses body waves and surface waves. The confining pressure is really just there to keep the interfaces pressed tightly together. So we, again, don't measure pressure effects. And with this setup, we can directly measure the shear modulus, and we can measure this attenuation that Miyake referred to, so the energy loss per cycle. So we torque it, and we can measure how much attenuation, how much dissipation, the same. So dissipation, attenuation, I use both words interchangeably. how much energy loss occurs over one of these cycles. So first, a step function application in stress. The key part is, before we were talking of strains of percent, right? Now we're talking about very, very small strains, right? Strains less than 10 to the minus 4, probably more than 10 to the minus 5. So we're in a linear regime here. And you can see a step function of stress as a function of time. The first thing here, we have instantaneous. So this is a measure of strain. Don't worry about the exact. This is just the fact that we have a cylindrical geometry here. That's just strain on this axis. So on application of a step function stress, we have an immediate response. And the immediate response, if you think back, way back at the beginning, right, that's Hooke's law, right? So if you compress a spring, you have immediate compression. So we have directly here elastic behavior. Then, of course, as we keep the stress on, we can see that we get this, in this particular 1200 degrees, we get this curve here, which a stronger curvature here initially, and then it becomes more shallow here. And you can see that perhaps better when we step the stress off. Right? You can see that the slope here of this curve changes. Right? So if you think about a Maxwell body, right? So Maxwell body spring and dashpot, step function in stress, you get the elastic compression of the spring, but then you would expect a linear behavior here. Right? Then just as you push a spoon into honey, right? You push this dashpot here, the longer you push, the more strain you get out of it, right, in a linear relationship. But that's clearly not what we see. We see a change in slope. Perhaps you can say that we have a linear relationship here, even though that's not true in the end, because we need much longer timescales to define that, to see that actually. But clearly here something else is happening. So from this part, it's very clear that a Maxwell body doesn't describe the deformation that we see here. Right? We need something else, and that something else is what's called anelastic behavior or transient creep. If you look at the Maxwell body, you have a spring and a dashpot in series. Here you have a spring and a dashpot in parallel. What that means is that you can't compress the spring instantaneously, right, because the dashpot will slow it down. On the other hand, you can't put an infinite amount of deformation into it with, hypothetically, here is an infinite dashpot, right? You just, as long as you push, you get strain. Here with the anelastic one, at some point your applied stress balances the spring constant, right? So what you have is that, you get strain accumulating rapidly, but then the strain rate actually decreases over time. At some point you saturate. And if you step off, if you relax the strain, right, the stress goes back to zero, you get all of your strain back if you wait long enough, right? Because the spring will just push it out. Whereas the Maxwell body, right, once you have imposed a viscous strain here, there's no restoring force. Right? So that's the key part of this anelastic behavior, this transient creep behavior, is that you have time-dependent but recoverable strain. Right? The strain in the elastic case is not time-dependent, it's instantaneous for our purposes. And then, on the other hand, the viscous strain is not recoverable. So here you have it both, time-dependent with a unique equilibrium state depending on the spring, and recoverable. Right? And in the end, if we do these experiments, this is what we measure. So here is the elastic, here is the anelastic part, and then eventually at long enough timescales, you have the viscous part. And we can describe that by a Burgers model, right, where we have to put this element in. And this is an idealized creep curve, so strain versus time. You have elastic, anelastic, and then viscous part. And the strain that's recoverable here is both the anelastic and the elastic strain. And then the viscous strain is not recoverable. And your total strain here as a function of time contains all three of these components. So time scales, and I'll come back to that briefly, right? So this is instantaneous, so earthquakes, immediate, that's actually brittle deformation, but in a low temperature elastic state. Seismic waves fall into this anelastic regime, and that came up a couple of times yesterday already, right? So we're at short time scales in this anelastic regime, whereas then post-glacial rebound is probably at the transition here, and mantle convection, we're well into the large strain viscous behavior. So attenuation, right? So again, something that you've seen before. If we then do, in order to get the anelastic part, it's much better experimentally to do this forced torsional oscillation instead of a step function and keeping the stress constant. We're sinusoidally varying the stress just like a seismic wave would. What we measure is shear modulus versus oscillation period. And you can see if you fix yourself at the 100 seconds here, so this is log scale, if you fix yourself at 100 seconds, you can see that the shear modulus is temperature dependent. Right? It decreases, so this is 800 degrees here. As temperature increases, the shear modulus decreases. So that's similar to what we saw in large strain deformation. The strain rate increases as temperature increases, right? So here the shear modulus decreases as temperature increases. More important, or equally important, I should say, is that if we fix a temperature and increase the period, right, we get a lower modulus. So if you look at 1100 degrees, the modulus systematically decreases at fixed temperature, fixed everything else, as the time scale of deformation increases. So time periodic, so here it is 1,000 seconds. The modulus at 1,000 seconds is much lower than the modulus at 1 second. Right? So everything else being constant. One aspect to keep in mind is that the grain size here is 3 micron roughly. If we compare two samples with different grain sizes, here is 23 microns, so not quite a factor of 10 in grain size. If you go to 1,200 degrees, you can see that the decrease in shear modulus, or that the modulus at the same temperature, is much higher at the coarser grain size. Right? So you clearly have a grain size dependence of this seismic behavior. Right? Everything else is kept constant. The only thing that's variable is the grain size. And so at the coarser grain size, you have a higher modulus than at the finer grain size. So the behavior is grain size dependent. And again, then we have to extrapolate, of course, to mantle grain sizes of millimeter to centimeter. Right? If we look then at dissipation, this is where we're getting to what Miyake was talking about yesterday, the absorption band. If you look at dissipation, exactly the same, so oscillation period versus energy loss, you can see, again, temperature, the energy loss is the least at the lowest temperatures. So at some point, if we have perfectly elastic behavior, right, there's no energy loss. As we increase in temperature, we get more and more energy loss. So we fix the oscillation period, increase in temperature, the dissipation becomes higher and higher. If you look at this as a function of frequency or oscillation period, you can see that there is a straight line here. So this is a constant, dependence of the dissipation as a function of frequencies, such that at 1 second here, we have the lowest loss at a given temperature, and it increases systematically with increasing oscillation period. Right? That's the same as what we saw here. We fix temperature, we vary the period, and the modulus decreases. This is the other side of the coin. The two go exactly together. The decrease in the modulus is directly related to the increase in dissipation. And that's this absorption band, right? This is this alpha that came up yesterday. That's the high temperature background. And you can see by varying the temperature, we have a fixed range of oscillation periods. By varying the temperature, we're really shifting this background, the absorption band, around quite a bit. Right? And again, we see a grain size dependence of this lower dissipation at coarser grain sizes. And the way, just very briefly, we can't just have a simple Burgers model. We basically have to have a superposition of these anelastic elements, right? We have to have many anelastic elements in series in order to generate this absorption band. So we end up with an integral here. So the total, this is basically the Burgers model here. The total expression for the Burgers model is a bit more complicated than that. It contains, though, the slope of this absorption band. And the background is, so going back to grain boundary sliding, right, we apply a shear stress across the grains. The shear stress, as you can see, tends to, in this simple thing, tends to rotate the crystals just a little bit. You get stress concentrations at the grain corners, and stress concentrations drive diffusion. Right? So we have diffusion as we get stress concentration at the corner. We drive diffusion away from these corners. So the stresses that we impose here are redistributed just as we saw for diffusion creep. It's very much the same idea, except that this is the scale of the grain corners. And this, again, goes back quite some time. So the first, this mechanism was proposed in the 70s. This is the stress concentration right after the application of the external stress. This is the stress concentration at steady state. So your stress concentration changes from the initial one at the grain corners to the steady state stress distribution along the grain boundary here. And that is a diffusive process. And that's a diffusive process that again goes back to the grain scale. Right? So you diffuse along the grain boundaries, and that gives rise to this absorption band. If you see this here, right, this just expresses the fact the more time you have, the longer your period, the further you can diffuse. So this gives rise to an absorption band, and you can actually model this. So if I step through this, this is now a model. I can't go into the detail. Stephen Morris at Berkeley, actually, and co-workers, some of his students and postdocs, this is the absorption band for this mechanism here, diffusionally assisted grain boundary sliding, which gives you a very broad absorption band. And keeping in mind this absorption band here, as a function of period, shifts around with temperature as well. Right? So this is at a fixed temperature over many orders of magnitude. That's the absorption band with this particular slope. Right? So that's the dissipation. We can calculate the slope here from these models. And again, I won't go into the details. This is this exponent alpha. We measure, as I said, a grain size dependence. If we look at the predicted alpha and the measured alpha, the grain size dependence, again, for grain boundary diffusion, right, is a cubic grain size dependence. The alpha is roughly about a third. So we get dissipation to be linearly dependent on grain size. And this is more or less, I won't go back to the experiments. That's more or less what we see experimentally. So again, this is obviously a model. We have some empirical evidence that this model applies and generates this absorption band. So if we look then at normal modes, right? So this probably is the wrong idea here, right? So there is grain boundary in here. This is what Miyake showed yesterday. We have, instead of all these different discrete absorption mechanism, we have one absorption mechanism. That's this diffusionally assisted grain boundary sliding, and the fact that it's distributed over such a broad time scale is due to the fact that the longer you apply the stress, the further you can diffuse. So that naturally gives you a broad distribution of time scales, and you can construct an absorption band from it. And so here, again, that is somewhere here, that's seismically observed. The interesting part is, right, so this is this alpha equals 0.3 here. They had in their work a decrease or an end of the absorption band, whereas clearly we're saying that this absorption band doesn't end, but it actually transitions seamlessly into diffusion creep, right? That's the connection between the small strain deformation from seismic waves to the convective deformation, right? This is the stress distribution goes from this after elastically accommodated grain boundary sliding to steady state diffusion. That's exactly what you see here. The continuum, one absorption band transitioning into large strain deformation. And the interesting part, so that's something we started working on, is that, so I flipped this here, right? So period increases now this way. These are normal modes. If you look at tidal deformation, right, and that's roughly aligned here, so that's 1,000 seconds here. Right, where the mode absorption band apparently ends in this is where you have the onset of tidal deformation. So deformation of the Earth, not by earthquakes, but by the effects of the sun and the moon. Right, so the shape of the Earth, very similar to modes, is also affected by the rotation of the moon around the Earth. So if you measure that deformation, you end up also with an absorption band. And again, you have this alpha here for a range of these measurements. And the tidal deformation, the interesting part is tidal deformation, of course, time scales of from 12 hours to, in the end, 16 years, 16-point-odd years, right? So you have an absorption band at much longer time scales. And again, the idea is, right, so to put that together, right, so here you have body waves, modes, tides, then you have small strain deformation also for post-glacial rebound, polar wonder, and then eventually convection, right? So you have a continuum of timescales at which deformation occurs. And that's, in the end, what we're trying to testing at the moment, whether you can really describe that with that absorption band. Right. So, yeah.
It's great that you're trying to link all these things, but aren't you sampling completely different parts of the Earth on those different time scales?
Well, this is the complication, of course, right? So, yeah, I can't go into all those details. So, yes, what we're saying, if you have an ideal mid-ocean ridge or back arc, whatever, that's partially molten, you can actually sample the intrinsic attenuation without having to worry about, similar to the experiment, right? In the experiment, we have one state in terms of pressure, temperature, dislocation densities, defect densities. In the Earth, of course, we have the radial structure. We have the structure, the degree 2 heterogeneity, for example, in the lower mantle. So all of this, if you then calculate the, if you then do the normal mode here, the tidal deformation in the modes, you have to take that into account, right? That's makes the comparison, of course, much more complicated, and I think that's a little bit behind why these models here. Clearly, this model for the modes, doesn't quite seem to be reconciled with the model for the tides, right? And the tidal guys essentially assume that's where their edge is, that's where their absorption band starts, is where their absorption band finishes. So the structure of the Earth obviously plays a large role in this.
Yeah, Uli. Yeah, I want to follow up on that. I think you're right. I mean, one of the for the students in the room, one of the challenges for making a measurement of alpha from normal mode attenuation is that different normal modes have sensitivities to different locations in the world, like Miyake showed you yesterday. Right. And so what we had to do to make that diagram up there is we had to kind of find combinations of modes at different frequencies that yielded the same dependence to Earth structure to eliminate that trade-off with depth. And to do so at the long periods is harder. And so that roll-off at to negative alphas at the long periods is really probably the least well-constrained part of that whole thing. Right. I think it suggests that maybe the Q measurements of the longest period modes should be remeasured. Or that there are some other factors that are coming in there. Because, for example, 0S2 has a similar sensitivity to radial structure as the tides.
That's exactly the idea.
And then it lines up nicely with a 0.3 alpha. So,
right. That's the idea a little bit. That in effect, if you look at the resolution kernels of some of the modes and compare them to the resolution kernels for the tides, they have very similar sensitivity to the radial structure, but at very different periods. So the idea is to compare tides and modes, but theoretically it gets very difficult, as you know, to calculate the modes, and similarly for the tides you have to have the same. In fact, the approximation that is behind this theory are very different. The treatment in the end is very different than the normal mode treatment. So you have to come up with the same theoretical treatment first. So in that sense, the lab experiments are much easier because we measured a well-defined intrinsic attenuation, whereas here, obviously, the structure of the Earth plays a very large role. So you have to get control of that first. And, temperature changes throughout. That's the same with post-glacial rebound. You're going from an elastic lithosphere into the, higher temperature part into the asthenosphere. So in order to get the time dependence, you have to take the structure and the variation in temperature and pressure into account. So it's a little bit more complicated, but in the end, the point is that the material that is deforming, right? That's, it's the same in the interior of the Earth. It's the same polycrystalline, the upper mantle polycrystalline olivine versus or lower mantle than bridgemanite, right? So in principle, and there has to be a continuum, right? It's diffusion, at different time scales. So.
Don't you have to distinguish at some point attenuation in shear and attenuation in compression?
There is very little bulk attenuation. So if you look at... there is some. Yeah, and Ian is doing bulk attenuation measurement, but that's on the scale of this exercise, the bulk attenuation is essentially negligible. There's so little in comparison to shear that I don't think we have to worry about it. But Ian is working on trying to do bulk attenuation as well. So we're out of time. What I had, of course, so very briefly to wrap up. So we can do the same experiment. We can look at now, the same experimental setup. We can look at the effect of water on seismic properties. And with the same structurally bound water, we can see that water leads to quite a lot higher attenuation. So water has not only a significant effect on the large strain deformation, but also on seismic attenuation. Again, the idea here is that both are linked, right? Both deformation, that the small strain deformation, the large strain deformation is linked. And then melt, I'll jump over that. So very quickly, the melt distribution, effect of melt and large strain. Melt has quite dramatic effects. One of the things I wanted to leave you with is that, the question whether you have melt or water on the upper mantle. So here's seismic properties at 1.3% melt versus 78% water. This is a very high water content for a stenospheric morph source upper mantle, right? So I'm not saying this is exactly realistic. The point is that experimentally, both water and melt have a strong effect on seismic properties. So unfortunately, we thought we could distinguish by doing these measurements between contributions from water and melt on seismic properties, but they both are fairly efficient in reducing seismic properties. So I'll leave it at that.
So along the mantle adiabat or isentrope, what's the relative importance of the delta V term in terms of creep, the fugacity term, and temperature? And I'm asking largely because of the strong pressure dependence of fugacity. And so, for example, do the experiments measure a large enough fugacity range that term is quantified well? And if it is, then down the adiabat, what's more important, the fugacity exponent or delta V or temperature?
So when you're talking, if you mean the water fugacity, so yes, the equation that I showed was for the water fugacity, but you can actually convert that into concentration. What we do measure in the end, so right, because we're at a constant pressure, right, we just vary, in effect, the concentration. We directly vary the concentration. This is one of the big differences to previous deformation experiments. You always, the experiments were always water saturated, so you could only get this exponent as a function of varying the pressure. Whereas we keep the pressure fixed and vary the water content. So in the end, we can, and there are ways of, there are ideas of converting fugacity into concentration. So in the Earth, most likely, in morph source mantle, right, you can, from the amount of water that comes out at the top, you can back calculate how much water there should be in the olivine. And that away from subduction zones in morph source mantle, the water content, the concentration should be constant. Right? So we can directly, in fact, write the flow law as a function of water concentration rather than fugacity.
Can you define fugacity? I'm sure some people don't know what it is.
The partial pressure, basically. So, the partial pressure of oxygen, hydrogen, and water in the end. So you can, it's closely related to concentration. For these, so it's easier to find those for gases and other materials. For solids, it's the activity in the end of water. In the end, it comes down to how much you have at a given pressure, right? So what I didn't show is you can convert fugacity into concentration, making some assumptions of the you have to look at the incorporation. In the end, it's incorporation of the hydrogen into the olivine structure. So there is an activation energy for the incorporation of that, which allows you to convert. So if we fix the concentration, or vary the concentration, we can write the flow law as a function of concentration of water, which we can measure for the mantle. Right? Then it becomes a bit more transparent. And then pressure effects, in the end, are taken up by that activation volume. Right? So, and I don't know whether you wanted to jump in or, okay.
Yeah, I had a kind of a general question. If in the future we know the seismic Q as a function of frequency in 3 dimensions, be optimistic, does that place some constraints on the long-term viscosity structure in the mantle?
If we know the water content, you're asking if we know that if we have exactly calibrated seismic velocities as a function of water content, and therefore know what the water content is in the mantle?
I'm saying if we know the Q from seismic waves
yeah.
in the actual Earth, in the mantle,
yeah.
you're relating the mechanisms of the seismic Q to the viscosity,
right.
very long times. So if we know the Q well, right now we don't know it that well, but
yeah.
if we do, does that place constraints on the viscosity structure
yeah.
of the Earth?
Yeah. So, yeah, I mean, that's a little bit what I was getting at here. There's some caveats, but yes, I mean, one of the interesting things is that if you look at Q as a function of depth and viscosity as a function of depth through the mantle, so in particular through the lower mantle, the two are really similar, right? And it's, the viscosity is estimated from post-glacial rebound and things like that. But the viscosity structure, not going into the details, but broadly, the two are consistent, and that's what I'm... The trends, yeah, and then different models, of course, there's some variability, but overall, the two are related, and that's what I'm getting at. So if you know the Q structure, you will have some indication of the viscosity structure. There are caveats such as, that's why I put up the power law creep, right? So if you have the viscosity and dislocation creep, when you have a power law dependence of strain rate on stress, you can vary the viscosity by varying the stress, right? So you're obviously then not directly mapping seismically, that variation in stress. You're mapping the variation in temperature and water content and melt, whatever is there, right? So there are some problems like that, but in general, yes, dislocation creep also depends on water content, temperature and so on. So yes, in a very broad sense.
I guess another pushback would be, yes, we know that, but we also do not know firmly, the grain size dependence. And so depending on not grain size dependent, the grain size, the true grain size in the mantle. Right. So depending on one mechanism or another, we'll have to scratch our head and assume some uniformity or non-uniformity of grain size in the mantle to be able to do that mapping into viscosity.
Right. So the grain size dependence, the handles we have is that where we have anisotropy, we know that we have to be in dislocation creep. We can't be in diffusion creep. So there's a little bit we can map out. I mean, that's not perfect, but at least where we observe anisotropy, it can't be pure diffusion creep, right? So, and the other side is what I mentioned earlier. That competition, the idea that the grain size is controlled by the competition between growth and grain size reduction. So then you end up, and then you look at grain sizes in xenoliths, for example. So yeah, but grain size is not very well constrained, particularly also going through phase transitions that are displacive. You have resetting of grain sizes and things like that. So we don't know everything perfectly. That's certainly true.
I think we should break for
okay. Yeah.
Thank you, Uli.
Yeah. At least to me, is this is a polarized light image, so you're looking through a thin section of a rock. You can see when the light is polarized, you can see the interference colors, and they look really beautiful. At the same time, it also reminds you that when I then go on and talk about spring and dashpot models, right, this is really what we're trying to model, right? So in particular, when we're talking about flow, right, you can sort of see that the olivine here, this is a single grain. The olivine is elongate. That's the expression of deformation, right? So the materials, when we, as I said, talk about spring and dashpot models, that's really what we're approximating. So that's a little bit in the background, right? The real materials are relatively complex. And this sample here, again, beautiful xenolith. This is a bit larger here. You can see the olivine pale green. Then you have some darker green in here. That's clinopyroxene. Right here is orthopyroxene. And then here, these shiny ones are spinels, right? So these are all in there. It's a polyphase aggregate. Whereas all the experiments will have a little bit of orthopyroxene, but for the most part, I'll be talking about olivine. So, right, jumping in from these beautiful minerals, to the very basics of physics. So Hooke's law here, the idea is that if you apply a force, then you get a strain out of it. So in physics, force and distance or elongation of the spring. In geology, of course, we talk about stress and strain. Essentially what I'll address in this talk is this spring constant here, right? So that's Hooke's law, is the proportionality between force and elongation. So twice as much force, twice as much elongation here. And what you're really measuring with this experiment is the spring constant. So if you apply that, so one important point is that the strain here, and I'll come back to that as well, the strain here is instantaneous and recoverable, right? So as you remove the force, you get all of your strain back. The spring goes back to its original elongation. More geologically, right, the same Hooke's law here is expressed as stress and strain, epsilon here, and then the spring constant are these moduli. Right? So Young's modulus more for engineering applications, and then what we are mostly interested in is the shear modulus, but also the bulk modulus. So S and P waves, as you know, depend on bulk and shear modulus. The crystal lattice, Jennifer Jackson covered that. Essentially, the positions of the atoms in the crystal lattice is from quantum mechanical, you can go back to as basic as you want here, is the potential here and versus the distance between the atoms is the result of superposition of a repulsive. So you have charged, if this is sodium chloride, you have charged ions, so you have repulsive energy and an attractive energy. And the superposition of the two, that's the smooth curve here, that has a clear minimum, and that's where your equilibrium position, that's the distance between the atoms in the crystal lattice. And that's important. You can see that the springiness might come from the fact that when you try to compress this, for example, right, you're trying to move here this equilibrium position, up the potential well, essentially, right? So that's the resistance. That's in essence very, very simplified where this elastic modulus, the spring constant, comes from. So deformation then, right? Here's Hooke's law again. Stress is modulus times strain. Here's the stress, here's the strain, the shear modulus, and you can clearly see that solids flow, right? You can't see that as directly with the mantle. You have to take plate tectonics from observations. But here, the glacier, it's pretty visual that you actually have crystalline ice, a solid, that flows. And you can calculate. So, right, the shear modulus of ice is roughly 4 gigapascals, 4 times 10 to the 9 pascals. The strain, just for order of magnitude, we just say a strain of 100%, so epsilon is 1. So basically here, the stress for the flow should be of the order of the modulus, right? That's what we're saying. We have clear deformation here, so if we deform a spring, we need to apply a force that overcomes the spring constant. But at the same time, you can calculate what the stress actually is, what drives the flow of this glacier. Right?
I'm a little bit confused. You use the word flow, and this is an equation without time in it.
Wow, okay. Effects in the first instance. And for that, we can actually look at very basic thermodynamics. Again, you've seen this diagram here before. The energy here expressed this time instead of the potential versus distance. And the energy of the crystal, so a system, in this case the crystal, it's the potential energy from the bonding, right? So sodium chloride, again, the simplest example, you have energy, that's the energy that's stored, basically the reduction of energy when you bring sodium chloride together. And in addition to that, we have, of course, temperature. And so we have kinetic energy. The atoms aren't fixed at their equilibrium positions, but they vibrate around in this potential well. Right? And that's essentially where an activation energy is coming from. The higher the temperature, the more they move around. So if you think about diffusion, where they have to hop from one potential well into the next, the higher the temperature, the easier it is to hop from one potential well into the next. So diffusion is temperature dependent. It becomes faster as temperature increases, right? So going back to the internal energy, interatomic bonding plus the vibrational energy. And then in the Earth, of course, that's a little bit the difference. to a lot of engineering applications, we also need to always consider a pressure. Right? There's always pressure increases fairly rapidly in the Earth with density. So that pressure also modifies the bonding environment or has an effect on the bonding environment on the internal energy. So pressure is always in the background here. So that's the internal energy, but the other part that we need is entropy. Right? So entropy, a measure of the disorder, and from the second law of thermodynamics, you know that entropy increases. So if you have a gas in one chamber, if you open up a valve to the second chamber, the gas tries to occupy all of space, or a different entropy is here, the configurational entropy. The entropy is at a maximum when you have this mixture of compound A and compound B. And one way to think about this, right, so here the entropy is very low. That's the parents' room. It seems very ordered. On the other hand, right, that's the maximum entropy here, the kids' room. Okay, good morning. So we'll continue today with rheology and building on what we've had so far this week. So I'll refer back to some of the earlier talks. So rheology, and you'll see how in this particular case I define rheology. It's actually quite broad, and I'll only touch on parts of it. Patrick Cordier, I don't know, will continue with this. I don't know where he's sitting. I saw him this morning sitting here. So he'll continue with this. So again, I'll refer to upcoming talks as well. I just wanted to point out, so this is work, long-standing work, that I'm collaborating with particularly Ian Jackson and then one of his current students, Chris Klein, at the Australian National University. So you'll see the seismic property work in particular is done by Ian and Chris. So outline very briefly fundamentals of defects. Why do we have defects? And I'll touch on some of the defects, in particular point defects. And then, as I said, line defects, that is dislocations, Patrick will cover. Then I'll point out something that's a little bit of a new thinking here, that there's a difference between intrinsic and extrinsic defects, and I'll define those, intrinsic versus extrinsic. Extrinsic basically meaning impurities. And in particular for water, the effect of water on the rheology and seismic properties, it turns out extrinsic defects, impurities in the olivine are very important. So the work that we're doing is pretty much all done on olivine, right? So that's more easily accessible, right? Perovskite, at least the silicate perovskite, is not stable at relatively low pressure. We do our experiments where we need to resolve stress and strain with very high fidelity at relatively low pressures, gas pressures, so we can't really work directly with things, bitumenite, perovskite, for example, or any of the other high-pressure polymers. Okay, so seismic properties then, continuing from that, and then I'll point out also something that came up in Miyake's talk yesterday. We need to account for continuum of relaxation times or for continuum of deformation timescales. So I'll try to cover all of this. Yeah, one aspect why this is so much fun, you'll see where this is going. So, sorry. So Michael was asking, I'm talking about flow, but this is an equation without time, right? So the point is, in order for flow to happen, I have to overcome the spring constant first. So I need to have a minimum force, basically, to overcome the spring constant. You'll see where this is going, right? So yes, this is not describing the flow. I'm just trying to get at how much force do we need in order to get the flow in the first place, right? So, so driving force is gravity here, and then we can calculate the pressure or stress is just rho GH, density times acceleration of gravity times the thickness, right? The thickness of the glacier. So density of ice, just round numbers, 1,000 kilograms per cubic meter, acceleration due to gravity. Let's assume a thickness of 1,000 meters, and then you get a stress that's about 10 to the 7 pascals, right, with these round numbers. So that's basically, you have to compare. Here's the spring constant, and here's what we actually have available to drive the flow, right? So there's clearly a bit of a problem here. We have 2 orders of magnitude, right? So again, what Michael was asking, we need to overcome the spring constant in the first instance in order to get flow, but apparently we have a really big problem, right? And the problem is even worse if you think about mantle convection. The minerals So olivine, for example, the shear modulus is about 80 gigapascal at room pressure and temperature. So they are of the order of 100 gigapascal. They get shear modulus increases as you go into the Earth with the polymorphs. But the convective stresses are of the order of 1 to 0.1 megapascal, right? So many orders of magnitude difference here. Megapascal 10 to the 6, gigapascal 10 to the 9, right? So we clearly have a problem. We can't, the perfect single crystal elastic constants can't be what's accommodating the flow in the mantle, right? And in particular, we need to modify these perfect elastic moduli. We need to have defects, right? They can't be, perfect, because otherwise nothing would ever happen, right? So that's the reason why we need to talk about defects. Where do the defects come from? Why do we have defects?